We'll begin our next informational Seeing the Unseeable, how we discover black holes shortly. Speaking will be Smadar Naoz, who is a professor at the Department of Physics and Astronomy at UCLA and studies a broad range of topics, including cosmology and black holes. Before coming to UCLA, she was an Einstein Fellow at the Harvard Smithsonian Center for Astrophysics. Professor Naoz contributes to diversity, equity, and inclusion through various activities and is dedicated to mentorship, having mentored over 50 graduate students and postdocs over the years. Please give her a round of applause.
Awesome. Thank you. I'm so happy to be here, and I'm always happy to talk here at UIU. So I am a theoretical astrophysicist, which means that I try to understand how the universe works. And my research spans a wide range of topics, from the formation of the very early galaxies all the way to the gravitational interactions of black holes and stars and even planets. And there is one thing that connects all of it together, which is physics, and specifically gravity at different scales. And this is what I think that astrophysics is all about. We're solving physics problems at different astrophysical settings and systems. So the system that I chose to talk about today is black holes. And specifically, I'm going to demonstrate or show you some ways at which scientists detect black holes. I'm going to talk about what we're learning from it, and then I'm going to ask all kinds of questions. So first, maybe we can start with the very first question of what is a black hole? Well, in a way, it's really easy to define a black hole. They have a mass, they have a spin, they spin around like ballerina, and they can carry charge. Black holes represent places in the universe that are so dense that gravity is so immense that nothing can escape from it, not even light. And we say that the place from which light cannot escape is the event horizon, and we call it the size of the black hole. If our sun would have become a black hole somehow, don't worry, it will not. But if it would, the size of the event horizon of the sun would have been slightly smaller than Santa Monica. And in fact, if we're thinking about LA City can represent a size of a black hole, which is about 30 times the mass of the sun. So its event horizon is about the city of LA. But don't worry, nothing's going to happen to us. We talked about what is a black hole. I want to say what it is not. So black hole is not a vacuum cleaner. Oh my God, it doesn't work. That was a joke. Here is the joke. Yay, now the joke worked. So it's not a vacuum cleaner. So all the black holes that I'm going to describe today, and all the black holes that I'm going to describe in our own galaxy, we're safe from them, so we don't need to worry. And I say that because once I give a talk about black holes, and a daughter of my friends didn't sleep the entire night after that. So we're safe. So not a vacuum cleaner. All right. So how do we see something that does not emit any light, right? I just said light cannot escape, but then how can we detect this? Well, because it's dancing. Some nice shining friend for the black hole is dancing around the black hole. So you know how the Earth and the moon are moving about each other. We always think that the moon is moving around the Earth, but they're actually moving about each other, just that the Earth is so big that it seems like the moon is moving about the Earth. And then the Earth and the moon are moving around the sun. Again, they're moving about each other. So if the black hole has a friend, the friend will move around it, and we can see it. So it will be very similar to something like that. Actually, we've seen something very similar to this. So what we see here, we see the star here, I show it in blue, and this is the black hole, and they orbit the center of mass, which is the center of gravity, where gravity is being balanced. And that represents a system that has been observed by a telescope called Gaia from the European Space Agency. And these type of systems that were detected completely puzzled us. This is not what we expected to see. And I want to explain to you why we found it so puzzling to find a system like this, right? A black hole orbiting with a star. And the reason is that this black hole is about 9 times the mass of our sun, and this is about a sun-like star, and they're orbiting each other every half a year or so. And it's strange because the way that we think these black holes form. So we think that these black holes are formed as a result of a very massive star that collapses. So stars burn hydrogen in their core. And as stars, even massive stars, so when I say massive, it's like 30 times, 20 times larger than the mass of our sun. And when a star like this exhausts most of its hydrogen in its core, it goes through a midlife crisis and expands a little bit. And the joke is in delay. So here we go. This star went through a midlife crisis. But what happens, and this is what we expect to happen exactly in such a system, is that the star, the one that will form the black hole, and this friend star are overlapping. They're actually colliding. And we expect them to merge and become one star. So that is very surprising. We would not expect a system like this to stay after the supernova and the formation of the black hole. Supernova is a big, big explosion that happens after the midlife crisis that a star undergoes. Now, don't worry, our sun will not go supernova because it's not too big, but it will have this midlife crisis and will become larger, almost eating the Earth, but the Earth will escape just by a tiny bit. All right, so I do want to say one thing more about this system. The way that they said that we have this dance around of a shining star around a black hole, this is actually not a new technique. This had been observed 2 years ago, something like that, with Gaia. But actually, the idea that we have this dance was used to discover a monster in our own backyard. And of course, I mean the supermassive black hole at the center of our own galaxy. And what you see here, this is a star that is orbiting an unseen companion, which is marked here with this little star. And as it moves about, we know that there has to be some mass inside, and we can estimate the mass. And this supermassive black hole was co-discovered by my colleague Andrea Ghez here at UCLA. So I want to highlight her because she received the Nobel Prize in Physics. She is the 4th woman ever to receive the Nobel Prize in Physics, and we're very, very happy. Yeah. We're still in a celebration mode here at UCLA for it. And this type of detection led to a lot of questions. Now we know that almost every galaxy hosts a supermassive black hole at its center, with masses between millions to billions times the mass of our sun. And we don't think that these monsters have formed in the same way that I showed you, like a big star that collapses and form a black hole. So that's a question that we still try to understand. So if you see it here, right, you see that this star, this one here, is coming pretty close. Actually, all 3 of them coming pretty close to this supermassive black hole. So we may ask ourselves, what happened when we come a little bit too close to a supermassive black hole? So here I'm showing an image of the Whirlpool galaxy, because it looks like a whirlpool. And I marked where the supermassive black hole is. I found it through Google Maps, for those who use Google Maps. And now let's see what will happen if I throw something to a black hole. So I have chosen to throw in my son, who is sitting here. But I chose a picture of him about 14 years ago. So, yeah. And maybe he did not clean his room, so he's been sent to the black hole. I run a very tough household. And now what's happened? I'm kidding. Now what happened? His room's a mess. But yeah. What will happen is that the supermassive black hole gravity is so intense that it's going to squeeze him. And it will squeeze him so much that it will make him as a spaghetti. It will spaghettify him before it will start to eat him. So, sorry, Ori. And in fact, it's not eating him very efficiently. So here is the Cookie Monster. So supermassive black holes are really like the Cookie Monster. They're not eating very efficiently. If you've ever noticed, the Cookie Monster is throwing away most of its cookies away. And that's actually really what supermassive black holes are doing. So here is an animation of a supermassive black hole here, and a star was thrown. And you see that the star is undergoing spaghettification, and lots of mass is being lost, a lot of gas. And that is exactly like the Cookie Monster. A lot is being spread outside. And that is really good, because we can then detect supermassive black holes this way. This is an indication that an unseen monster is eating a star there. And that's not an easy thing, to bring a star so close to a supermassive black hole. So my student Denise Melchior and a former postdoc, Brenna Mockler, are few people of my group that are actually working on trying to understand how do we throw stars into a supermassive black hole. And I want to highlight Brenna, who did so well, and now she is going to be a professor at UC Davis. So I'm so proud of her. I'll tell her that you got all these claps. I think that she will be very happy. So the fact that there's so much gas there means that there is another way to detect this supermassive black hole. You may have seen this image before, this donut. It's not a real donut. It's actually the gas that becomes so hot around a supermassive black hole in a galaxy called M87. And scientists in the Event Horizon Telescope were able to construct this image by looking at this M87 for more than a year, and were able to analyze the radio emission that comes from this very hot gas around the supermassive black hole. This supermassive black hole is 1 billion times, a little bit more, than the mass of our sun. This galaxy, M87, is eating so inefficiently that it's actually throwing away a jet of gas, of material like that extends over more than 1,000 light years. That's 2 ways that this galaxy tells us that there is a supermassive black hole in. It throws in a jet, like a huge cookie, if you think, and also there's so much gas and it's so hot that we are able to detect it. Another 2 ways to try to see it. And again, the understanding of how so much gas is there and how do supermassive black holes grow if there's no like superstar that make them. This is an active research that we're trying to understand. So a question is, indeed, how do we feed black holes? And interestingly enough, it's not just big black holes that like to eat. It's also small black holes that like to eat. Those black holes that I said that are forming from stars that collapse. So the question is, how do we get a black hole that will eat its friend? So the first thing is that we need a friend. So maybe the first question that we ask ourselves, is it common that stars have friends? Well, certainly it comes in the movies. Who recognized this? Someone help me. Who recognized this? Yeah. Star Wars. Yeah, this is Tatooine from Star Wars. Here is Luke Skywalker. There are 2 suns. His planet is orbiting 2 suns. So indeed, in Hollywood, it seems like stars like to live in pairs. And actually, this is also in reality. Stars are more likely to have a friend. In fact, our sun had a 50-50 chance to have a companion. And we can think about it later, whether or not it's a good thing or a bad thing that our sun doesn't have a stellar companion. Massive stars, those that will become black holes, most of them, if not all of them, have friends. Right, so that's good. So now I can start with a friend. I'll have one big friend going through its midlife crisis, so it's expanding. And if, and that's a big if, it did not collide with a smaller friend, then it will explode, undergo supernova, and make a black hole. That's good. There's a little bit, few more details here that we calculate. And yeah, and then we need to wait for the smaller friend to undergo their midlife crisis. And what's happened next is that it became a little bit too close to the black hole and gotten eaten. And we see what happens then. We see it as X-ray, just like the X-ray that we go and take. I've taken X-ray last week. I busted my knee. I had to go and take an X-ray. I'll recover. But this is exactly the same thing. It's become the gas around the little black hole. This is about 9 times the mass of the sun. The gas around it is so hot that it emits an X-ray like this. And this is an animation of a very famous X-ray binary, this is how we call them, called V44 Cygni. And the reason it's so famous is because it's one of the first ones that were detected. These things were detected since the 1960s, were the first black holes ever to be detected. And you see here 2 pictures of my students. One of them was an undergraduate student, Shayan Shariat, now is a graduate student in Caltech, and Ziyuan Shuan, who is going to graduate with his PhD really soon. And they work on systems like this. And interestingly enough, this system is actually a triple. It came too fast. It's actually a triple, so there is a 3rd star orbiting them. And that will play a role in a minute again. The 3rd way I want to mention is gravitational waves. And you may have heard gravitational waves. And gravitational waves are ripples in space-time that happens when 2 things accelerate toward one another. So I'm going to accelerate toward you. And because I busted my knee, I'm not accelerating very well. And I emitted just a tiny bit gravitational wave, and it's nothing because we're not weighting so much. But 2 black holes that accelerate toward one another, they emit a lot of gravitational waves. And when they collide, for a brief moment in time, they shine more brightly than all the stars in our universe combined. But they do not emit their energy as radiation. Instead, what they do is emit it as gravitational waves, like these waves, like a wave in the pond. And space-time really doesn't like to be perturbed, doesn't like that something like that happens. It's very stiff. So the changes here between the valleys and the peaks are 1 with 21 zeros, one part of 1 with 21 zeros behind it. This is how small it is. And these type of systems were detected in 2015 by LIGO. And forever transformed the way that we sense our universe, because we no longer rely on the electromagnetic spectrum. And now we know that we can sense our universe in a completely different way. We have 2 LIGOs in the US, and you may ask yourself, why do we need 2? It's the same reason that I need 2 eyes to judge distances or 2 ears to judge distances. The other interferometers around the world, part of the collaboration, are not as big and strong as our LIGO, and therefore we need to, and I'm saying it because they're under danger to be decommissioned. What LIGO taught us is that there are a lot of black holes that are merging. Here is a black hole merging with another one. So this vertical axis is the mass of the black holes. This is nothing, just to make it pretty. And then we see black hole, and another one. And what I want for you to take away from this is that there are so many In fact, LIGO estimates that every 15 minutes, two black holes merge. So since I started talking, at least one merged. And by the time we will be done, there will be another one. So that's pretty impressive. And it's even more impressive that if we would go back in time before 2015, before LIGO even detected one single black holes that merge, and you'll ask astronomers, how many black holes will LIGO see that are merging? They will tell you 0. People really thought that there'll be nothing. And the reason is, remember how I kept on saying, if this star will not collide with this other star? It's because it's really hard to get these things to merge. And this is another thing that many of my students are working on in trying to understand, how do black holes collide? And that's another question that we're working actively in my group. So I've described 3 ways to see stellar black holes, to detect stellar black holes in our galaxy and in our universe in general, right? This thing that emits a lot of X-rays, this thing that emits gravitational waves, and this one that is dancing around its friend. And a question that we can ask ourselves, whether or not these are completely different systems, they're forming differently, or there is some connection between them all. And I would say that there is a connection between them all. And the reason that I say it is because one more strange thing that black holes do when they merge. Black holes not only are born in pairs, in fact, they're born in triples. So for those who know me that are here, know me that I'm really obsessed with the 3-body problem. And the 3-body problem is a fundamental problem in physics, and it's gained a lot of interest recently, a little bit because of the books and the show. And just a little spoiler, if you haven't seen the show, it's a good show, and the books are really good. The books in the show are actually the 4-body problem, not the 3-body problem. So it's not exactly the same thing, but okay. But what does this triple does? This triple actually changes everything. And the way that it changes is because I have now a pair that is going to collide, become one, right? I'm going to make this into one black hole, and something's going to happen with this other star. And that relates to what happens when stars merge. So here is a simulation of 2 black holes that merge. You can see them here. And what's going to happen when they merge, they're going to emit a lot of gravitational wave, and that's going to kick them. So here it is, it's about to be kicked, and shloop, it kicked. It's actually a little bit like an exhaust on a rocket. So this new black hole that merged now is being kicked out of the picture. So now if I'm going to kick this new black hole, we showed that it can easily make these type of black holes, of a dancing black holes. It can easily make these X-ray binaries, and it can also create a shredder that will shred the star in some cases. All right, so what do we do in my group? I kept on mentioning my group and my group this and my group that. So we look at different puzzles, and we try to ask all kinds of questions and then to disentangle between these questions. And we make predictions to test these for LIGO, or maybe the next generation gravitational wave detector, and maybe also with the electromagnetic signatures that we can detect either using Keck or Hubble or JWST. And since I mentioned my group, I want to show you them. I like to work with a lot of people. And apart from posing very nicely in a professional manner, we also have a lot of fun together, often involve food, sometimes involve silly hats, like here. And we really like Halloween, so you can see us dressed up. And that's it. If you have any questions, I'm happy to take them. Yes. Yes. So an unexpected finding, for example, was this black hole that is orbited by the small star that I mentioned. This is something that no one expected whatsoever to happen, because we expected that the progenitor of the black hole, the star, to eat and to collide with a smaller mass star, and it was really unexpected that we will detect that. And then the fact that it is there made a lot of people try to figure it out. And I think that what I showed you, this kick, is one of the good answers. But I'm very biased because I came up with this idea. Yes. What if two supermassive black holes collide? What an excellent question. Well, when they collide, they emit gravitational waves, just like the littler black holes. And then we hope to detect these supermassive black holes that will collide. We hope to detect them with the space-based next generation gravitational wave detectors. I showed it before. Sorry, I didn't hear. Yeah, if they combine. If they combine, they make a new black hole. And you know what happened when they combine and make a new black hole? Then they get a huge kick, and they may even escape the galaxy, which is pretty cool if you think about that. It's a very good question. The question is, what's inside a black hole? If you go into the black hole, what's in it? We don't know, because nothing can escape a black hole. So we really don't know. We're trying to formalize a new mathematical understanding of how really to understand what's inside. These are big, big questions. My suggestion is maybe you should study hard and come and join us and help us out. All right? Yes, you had a question? It's okay. Yeah. Yeah. Is a black hole able to suck up a solar system? Theoretically, yes, it can. If somehow I can throw in a solar system, it will start to eat the solar system planet by planet, starting from the most outer planet, and it will be eating them one by one. So yes, definitely. Yes. Oh, excellent question. So how long does a midlife crisis take for these stars? So massive stars, they live fast and die young. So so our sun, for example, is about 4 billion years old, 4.5, and a star like this that will become a black hole after about 10 million years. It will undergo this midlife crisis. This will be super fast in astronomical terms, meaning it will take it about 10,000 years to do that, and then it will explode and will become a black hole. Yes. Oh, it's a good question. What is a white hole? A white hole is a hypothetical idea that says that maybe not only we have a black hole, but we have some place, a white hole, where we can connect and move all the material from the black hole to the white hole. In order for this to work, we need to imagine a little bit more things like extra dimensions or different gravity. So these are things that we try to understand, especially because we don't know what's inside the black hole. So I'll make the same suggestion to you. Study hard and come and help us figure out, okay? Yes. What was the first black hole to ever be discovered? Very good question. It was an X-ray binary, just like these ones that I showed you, right? It was a black hole that was eating a star. All the gas around it became very, very hot, and then it emitted X-ray. Very good question. Yes. It's okay. Oh, that's a good question. How does how does stars born in triples? How does stars that will make a black hole born in triples? So the idea that we have for star formation is that we start the gas cloud that collapses due to its own gravity. In order to make a star, we need to make sure that there is a lot of mass in it, especially if I want to make a massive star. So that means that I have a very massive cloud, and it will collapse and will create more and more pockets. And each pocket like that can make a star. And these very big stars will have 3 pockets or even more. So this is how we create stars and triples. You had a question. Yeah. What determined the direction of the kick? Deep and tough questions from my son. So the thing that determines the direction of the kick is actually a calculation done in general relativity. And what happens is that you have 2 black holes that are orbiting their center of mass, and the lighter one is moving faster. I think I actually have a plot here to show it. The lighter one is moving faster than the more heavy one. And what it will do is that it will create that emission will be larger at one specific direction. Yeah, this one. So this is too small, sorry. But what will happen here is that you'll have that, right, the lighter one is moving faster, the heavy one is moving slower, and then you have more emission that will come in this direction because of this lighter one. So the final direction of the kick will be directed this way. Yes. Yeah, you. Yeah. Oh, that's a nice question. What if 2 stars collide? Will they become a supernova? So if they are very massive, they collide and make a new star, yes, they can make a supernova, and it will be bigger than before. Yes. Oh, very good question. What if the sun had a friend? So in fact, this was something that bothered a lot of researchers, including myself, because what a friend can do, if the friend is, and in fact, actually, Ling Feng is here, and Ling Feng was an undergraduate exchange student that worked with me on a similar problem. The idea is that if you have many, many planets and they're very close one to one another, then they basically keep each other safe from a friend. But if there is some distance between them, then it's not very safe, and everything can collide, all the planets. And that depends how close the friend is. So if a closer friend can destabilize, and we wouldn't be here. But if the friend is far away, we wouldn't care so much. Yes? Oh, that's also a good question. Does a black hole a sphere or a disk? It's actually a sphere. And the reason that I show it here as a disk, because I'm showing something in 2D. Yes? So that's a very good question. How do we get the radiation? And I assume you mean the gravitational wave radiation, if nothing escapes the black hole. So it's not coming from the black hole itself. It's coming from the acceleration of the 2 objects. And I did this demonstration a second ago in the middle of the talk, and I'll do it again because it's a bad demonstration. It's happen every time that someone is accelerating. So I'm going to accelerate toward you again. And I accelerated not very impressively, again, I know. But I've emitted a little bit, a tiny bit of gravitational wave, a minuscule bit. So we cannot actually see it or detect it because we don't weigh a lot. But 230 times the mass of the black hole that approach each other so much, they perturb the space-time. So the emission doesn't come from the black hole, it comes from the act itself. All right, if no more questions, thank you, everyone. Oh, come.